Okay, time to get started. So here's what we were talking about last time. We were talking about this theorem right here. Talking about, suppose you have a linear transformation. We've said a lot of stuff about linear transformations in the last couple of days. Specifically, though, here we are talking about a linear transformation with a finite dimensional domain. Important asterisk that we need to make sure to put on this theorem. Okay, remarkable punchline: the kernel and the image, even though they live in different worlds, right? The kernel lives in the domain, the image lives in the target, different worlds, but their dimensions add up to the dimension of the domain. Very weird that this works out. Well, very weird at a glance. So I want to remind you the proof, air quotes, that I gave you of this last time. It's not quite complete. There's a little detail, of course, that I confessed to last time that I'll, fill in the next, we got spring break in about 45 minutes here, right? But very soon after that, we'll fill in this blank. So I'm going to proceed as if this blank is filled in, and I'm actually going to fill it in after spring break. But so the big idea is, in fact, every one of these linear transformations with a finite dimensional domain, every one of them can be viewed as a matrix. Now, again, details to come after spring break. So, if we're looking at a matrix, then all of a sudden this problem changes dramatically, right? Given a matrix, viewing a matrix as a function, we saw last time that the kernel is the null space, right? And we saw last time that the image is the column space. And, notice here the dimension of the domain, there it is. Dimension of the domain is n. Right? So in order to prove this theorem that we're interested in, all I have to actually do is prove this theorem. Oh, wait, we already know this equation holds, right? This is, you can call it by different names. Rank nullity theorem is the name I like to call it. But we already know from chapter 2 the dimension of the null space plus the dimension of the column space is equal to the number of columns. So neat fact, right? So the proof of this result actually boils down to observing that we really pretty much already knew it. Okay, moving along now to a corollary of this. In order to be able to state this corollary, I have to talk about a function that is what we call bijective. Bijective is a single term that refers to both one-to-one and on-to. Y'all may or may not remember these terms from Calc 1 or Calc 2. It depends on how topics are ordered. Certainly in a single variable calculus course, you should have seen these. I am aware that you might not have. No problem. If you haven't seen these, I'm going to say I recommend that you go ahead and give them a look. All we really need to know is what does it mean for a function to have both of these features, to be bijective. And bijective is a little bit easier to describe. It just means that a function is a perfect pairing between the domain and the target. If you got your domain over here, your target over here, the function, for every input, there's exactly one output. For every output, there's exactly one input. It's kind of the buddy system function. Every output gets paired up with exactly one input. Okay. All right. So if you have one of these perfect pairing functions, and if that is a linear transformation, so linear transformation that's bijective, then a corollary of the above theorem is that the domain and the target have the exact same dimensions. Now let me give you an argument as to why this follows from this above theorem. It's not that big a deal ultimately. I'm going to make a kind of a rough, theoretical picture of our situation here. Here's our V and here's our W. And we've got our function t from V to W, sort of a figurative picture here. And now keep in mind, we're considering a situation where this linear transformation is a perfect pairing. And so for every input, there's exactly one output, and perfect pairing, they line up 1 to 1 like this. Really the best way to say this, we know that for every input, of course, there has to be a well-defined single output that is the output value. The best way to say this is that for every output in the whole target, there is exactly one corresponding point in the domain that hits it. Okay, so this is a picture of our function, and let's think through now, well, what does this theorem say in this case of this bijective linear transformation? And let's start with the kernel. What's the kernel in this case? Well, keep in mind the kernel is, what lands on the 0 vector? Let's suppose that you've got the 0 vector there in the target. Well, what lands on it? I mean, this is a perfect pairing function, so there's exactly one vector over here. Turns out it is, in fact, just the 0 vector. The fact that it's the 0 vector itself isn't really the point. The point, though, is that it's a single point. No pun intended. So the kernel, this kernel is just a single point, and the dimension of a single point is 0. So in this scenario, our kernel, let me color code this, our kernel, being as it is a single point, has dimension equal to 0. Okay. Right, so now let's consider, what about the next part of this, the image. What's the image here? Well, the image is the collection of all actual outputs. Remember the actual set of actual outputs that come from actual inputs. Well, again, perfect pairing, right? For every output, there is exactly one corresponding input. Let me say that a little bit differently. For every output, there is some input that hits it. Therefore, every point in the image is also a point in the target. Let me say that backwards. For every point in the target, that's also a point in the image. Every point in the target is the image of something. So the image is the target. This image here is W. It's the whole of W. So, altogether, look what our theorem says. We're actually done here. It says that other than this 0 over here, which of course doesn't matter, it says the dimension of W is equal to the dimension of V. It says, therefore, that the dimension of the target is equal to the dimension of the image, and that's what we were going to prove right here. So that proves our result. So, nice corollary. Turns out this corollary is going to allow us to do some really nice things. Saves us loads of trouble momentarily. Let me go ahead and show you the loads of trouble that it saves us on the next page. We're going to call back to chapter 4. We were looking at linear differential equations. I made this observation that when you have a homogeneous nth order differential equation with various regularity constraints, the existence and uniqueness theorem conditions being satisfied, that in this situation that the set of solutions was an n-dimensional vector space. I asserted that, and the book proved it at the time, and the only thing is proving that back in chapter 4 with the tools that we had available to us in chapter 4. It's a pain. You don't believe me? Take a look and see the book's proof back in chapter 4. The book's proof that this set of solutions is n-dimensional. It's kind of tedious. It's unwieldy. There's a lot of little micro details. It's a long, opaque conversation. Okay. So we now have much more powerful tools. We are now going to be able to prove this very quickly, I'm going to say. We're going to wave the magic wand of linear transformations and theorems that we know about them, and this is going to fall in our lap. So here's how that goes. It's a wonderful argument. Goes like this. Don't forget, We do already know that this set of solutions is a vector space. That we proved. It was a subspace and therefore a vector space. Side note, here's another vector space we know. If I look at the set of initial values, remember we talked about these things called initial value problems. An initial value problem is a differential equation paired with a set of initial values, or you might call them set of initial conditions. And I'm just going to make the observation that what initial values are, really, is that's a vector in Rn. See, here you go, a set of initial values, right? This is what a set of initial values looks like. It's a value of the function at x equals 0, a value of the derivative at x equals 0, a value of the second derivative, the third derivative, et cetera, all the way down to the n minus 1 derivative. That's what an initial value looks like. Well, I mean, modest observation, being as those are all numbers, what we have is an n-tuple. We have ourselves a vector in Rn. So, it's also a vector space. Right? The collection of all initial values is literally Rn. Rn is a vector space. Okay, now, it's not clear where this is going just yet, so bear with me. I'm going to define a new linear transformation. This is where we start to capitalize on our new tool for today. So my linear transformation here is called T, and T goes from my set of solutions to my set of initial values, aka Rn, as follows. If you give me a solution to the differential equation, the value of my linear transformation is going to be, well, whatever the initial values are for that solution. So you give me a solution, I can take that solution, compute whatever necessary derivative, plug in x equals 0, and get my initial values, and that's what this linear transformation does. So it's kind of like, y'all may recall, we proved I left as an exercise for y'all to prove as a linear transformation the Dirac delta function, or the Dirac delta distribution, depending on how you like to say it. That's really kind of not that different from what this is. It's, it takes some derivatives beforehand, but pretty much plug in x equals 0 into the function and its various derivatives. Easy to check that this is a linear transformation. Now, you got to do that. Little details for y'all, right? Good exercise, good practice. Give that a shot. Okay. We have a linear transformation from a vector space to a vector space, from a domain to a target, right? Not hard to convince you, I hope, that this linear transformation is one-to-one and onto. This linear transformation is bijective. This linear transformation is bijective. For every output, there is exactly one corresponding input. Now, I want to show you a picture. Let me remind you what a bijection looks like. A bijection looks like this. For every output, there's exactly one corresponding input. Now, there's a picture that I've got drawn over here. Side note: this page of lecture note. This is not in the PDF file, the big PDF file. This is a supplemental page that I wrote some years after the big document of lecture notes. But this is on the Sakai site in the resources section if you want to have a copy of it. And this is just kind of a graphic sort of visual aid of what this linear transformation looks like. Here's the domain, if you will. Solutions, right? Actual functions. Y is a function of x. That's what solutions look like to our differential equation. I've drawn one such solution. Right? So that's going to be my domain, set of all solutions. The target is, as I've got drawn here, the set of all initial values. Just to represent it in the picture here, there's the value of y at x equals 0, but there's only so much I can draw on the picture. The initial values are, in fact, the value of y and the value of y prime and the value of, et cetera, all the derivatives. Okay, so kind of a sort of a picture. In purple are my domain vectors, namely solutions. In blue are my target vectors, namely initial conditions. You give me a solution, I can plug in and compute for you the output, namely the initial conditions. Okay. So I claim that this is a one-to-one and on-to. I claim that this is a bijective perfect pairing function. So again in red here, you give me a solution, I gave you an initial condition. Claim this is a perfect pairing. So what I mean by that, again, is for every output, I claim there is exactly one input. Let me say that a little bit differently. For every set of initial values, there is exactly one solution, I assert. For every initial condition, there is exactly one solution. Okay, now let me say that again a little bit differently. For every initial value problem, there exists exactly one solution. We already know this, right? This is the existence and uniqueness theorem. It's one of the first theorems that we wrote down back in chapter 4. For every initial value problem, certain conditions being satisfied that we're assuming here. For every initial value problem, there exists exactly one solution. So, what that is saying, as it applies in this context, is that that function t is a perfect pairing. One-to-one and on-to, bijective, however you want to say it. Okay, so that observed, it's really all over but the shouting at this point. Let me go back to the statement here. This function is a perfect pairing. This function t is a perfect pairing linear transformation, and I remind you that when you have a perfect pairing linear transformation, the domain and the target have the same dimension. That was our big result from this page. Domain and the target have the same dimension. Well, what that means, is that the set of solutions has the same dimension as the set of initial values, which we've already agreed is Rn. Right? So therefore, the set of solutions has dimension n. Very powerful argument. We sidestep a lot of the little details and ugliness in the book's proof in chapter 4, and we just invoke the big gun on the previous page, and there we go. Okay, so much nicer proof. Now let me acknowledge there's some subtleties in this, right? You've got to kind of wrap your brain around the idea of this weird linear transformation. We're accustomed to linear transformations going from, Rn to Rm, perhaps, right? We're accustomed to being able to think of vectors as, long, pointy things, right? So here I'm doing something a little bit more abstract. I'm using critically an abstract vector space of solutions to a differential equation, and doing a weird linear transformation on it where I do this. Well, the details are all here, but a certain amount of abstraction and oddity in the setup. But once you've got it set up, it's an immediate consequence of known big theorems. Okay, so that's a loop that I've closed, right? I've owed you that. I've needed to close that loophole for the last month or so, and we've now got that resolved. And moving on to the next section. 5.1 was a long section. We're finally through it. On to section 5.2. 5.2 is another section that has a fair amount of build into it. So we're going to have to lay a certain amount of groundwork, but there's going to be very powerful punchlines at the end of section 5.2. And let me just, so you know where we're going with this, I'm going to be able to prove several things from chapter 4 that we kind of deferred at the time, but I'm going to be able to prove those using powerful ideas that we're about to set up here in section 5.2. So just to let you know, you remember that theorem when we were solving homogeneous differential equations? And the theorem was if you have a root of characteristic polynomial, and if that root has a multiplicity, then mysteriously, magically, you just start multiplying by x for no apparent reason, and it just works, right? We're going to be able to prove that here in this section. Likewise, that wacky theorem from section 4.3, the great big theorem that says, here's the magic guess that just works, right? You have your naive guess and your magic number and the unfortunate coincidence, and then you multiply by x to the m for reasons that were never explained. And then, poof, it works, right? We're going to be able to explain why that is. All that's coming at the end of this section. Okay. All right, so the build. We're going to talk about what we call an algebra of linear transformations. Sounds like an odd construction. What do we mean by an algebra of linear transformations? Algebra that we've done in the past was, well, algebra of numbers, right? X squared plus 2x plus 1. The elements of your algebra were numbers. So algebra of numbers is what all of high school algebra is pretty much algebra of numbers. Okay. We expanded on that earlier in this class, and we started talking about an algebra of matrices. Now that was weird. Matrices aren't numbers, right? Matrices they're a shorthand for a system of equations which involves numbers, but a matrix itself is not really a number. But we talked about, nevertheless, a way to think of matrices as them, and forget about the whole systems thing, to think of a matrix as an elemental thing, and to talk about what it might mean to add two matrices, and what might it mean to multiply two matrices. And turns out we were able to come up with definitions of those things, and we had a whole algebra of matrices. There's a distributive law of matrix multiplication, etc. Right? So we're going to do the same thing now with linear transformations. Seems weird, but we're going to think of linear transformations as objects, not as functions that deal with objects, right? But we're going to think of linear transformations themselves as objects. Very strange, but here we go. If you have two linear transformations. Oh yeah, question.
Sorry, yeah.
Yeah.
So a few pages back we said that the linear transformation of finite element should make it written as a matrix. So if we kind of define the linear transformation as a matrix, won't the algebraic properties essentially be the same?
That's a great question. You can take a point of view like that, but I'm going to take a slightly different point of view, and then I'm going to revisit that after spring break. But that's actually a fantastic question and very insightful. Yeah. So I don't want to give away the answer to the question just yet, because giving away the answer there will mess with my drama after spring break. But very good question. Thank you very much. And I feel bad for not answering right away, but the answer is coming. Yeah, exactly. Okay. So let's ignore that excellent question momentarily. Don't look behind the curtain over here. Okay, so we've got a couple of linear transformations. And notice we can talk about what it means to add those things, right? Now, don't think of these as functions anymore. Think of these as elemental little atomic kind of objects. And now we're talking about what it means to add these two objects. We have to remind ourselves, we've actually kind of done something like this before. We talked about vector spaces of functions, and we've already defined what it means to add two functions. Here's how you add two functions. Likewise, what does it mean to multiply a function times a scalar? Well, again, we did this back when we were doing vector spaces. So these little bits of our algebra of linear transformations, how to add them, how to multiply by scalars, we already have those. Sweet. Just as a point of order, notice we kind of stole these. We stole this notion of addition of linear transformations from this addition right here, that being the addition in the vector space W. Right? So in some sense, we're using a vector space addition in the target to define a new algebraic addition on linear transformations. Okay. Likewise, this scalar vector multiplication, we're taking that existing scalar vector multiplication out of W and we're using that to define now a new multiplication. This is a scalar times linear transformation multiplication. So we're kind of stealing that. So the reason I'm pointing this out is I want to address the next question of how would I multiply if I want to multiply linear transformations. Can't I just do the same thing? And the answer is no. I don't have a vector multiplication inside of W. That's not a thing. Right? W is a vector space. You've got addition, you've got scalar multiplication, that's it. There's no product in W, therefore I can't steal it because it doesn't exist. Okay, so when we define multiplication, we're kind of on our own. We've got to do something completely different. Here's what I'm going to call a product of linear transformations. The short version is I'm going to say that a product of linear transformations is a composition. And don't forget, we define compositions by how you evaluate them as, well, take the output from the one function and put it into the next function, right? So this is the same old composition that we defined back in Calc 1 when you're learning the chain rule. It's the same composition. What comes out of one goes into the other. Okay, so seems weird, but I'm going to call that a product. I want to recognize it doesn't look like a product. It seems pretty fishy that I should call it a product. In what sense is this a product? You might be asking yourself. I hope you're asking yourself. Why is this a product? What gives? On this page, there's really no good answer. There's nothing about this that makes it look like a product. What makes it look like a product is what's on the next page. When you take these operations and start writing down properties, all of these properties are true. The addition that I defined on the previous page, the multiplication of linear transformations that I defined on the previous page, the scalar multiplication that I defined on the previous page, those operations all satisfy these 9 properties. And do you notice they look familiar, right? I mean, it's good old algebra. It at a glance looks just like 8th grade algebra, right? There's a distributive rule on both sides, and there's sort of an associative property, and there's a different kind of distributivity, another kind of distributivity, and a couple of different kinds of associativity, and it's just a bunch of familiar looking stuff. You could see yourself just doing all sorts of algebra with linear transformations at this point. And in particular, notice what we defined as a product behaves within this algebra, behaves like a product in the algebra. So we call it a product, right? For lack of better ideas. So there you go. Now I do want to point out one thing that's missing. Notice multiplication is not commutative, right? That's a big no right there. Composing functions, in other words. It matters which one you put into which one. I don't think that's particularly surprising, right? Think back to some old easy Calc 1 examples. E to the power of sine x is just not the same as sine of e to the x. They're just different, right? So not commutative. That's sad. Keep that in mind. Don't inadvertently step on that landmine and accidentally commute things around like you're allowed to do that. You're not allowed to do that. Oh, wow. Okay, but these 9 properties here, all true. Each one of these deserves a proof. I'm going to give you one. I'm going to prove this one for you. The rest I encourage you to prove on your own. You'll kind of see how it goes down, proving number 8 here. And the way you're going to prove the rest of them is analogously. So I don't actually suggest that you prove all 8 of the remaining. pick a couple of them. Write down the proofs of a couple of them until you feel like, okay, I see how this works. I can do the rest of them. And then don't actually do the rest of them. Okay, so here's the proof. I'm going to prove that this is equal to that. Specifically, I want to prove that the function defined by this little formula is the same as the function defined by this formula. Now, strategy for how to prove these two functions are equal is I'm going to plug the same vector into both of them, and I'm going to compute both of them, and I'm going to confirm that I get the same thing out from both of them. And that proves that they are equal as functions, right? If you have two functions that have the property that whatever you plug in, you always get the same outputs, those are the same function. Yeah? Plausible? Okay. So all you got to do is just be careful and follow the rules here. There's no tricky curves in this proof. Notice first I have a product of two linear transformations. We have a definition of product of two linear transformations. You plug in. So whatever comes out of the first one, you plug that in to the second one. So this, rewriting that as that's just the definition of multiplication of linear transformations. 2 pages back. Okay. Now notice I have an addition. I have that plus this. What does it mean to add two linear transformations? Well, what it means is whatever it is that you're plugging into that sum, plug it into each one individually, right, as you see I've got here, and then add the results. So again, all I did in going from this step to that step is I just followed the rule of the definition of this addition operation right here from 2 pages back. And having done so, I've got a formula for how to compute this thing. I'm going to leave the remainder for you all to read on your own, but it's the same deal. I'm just follow the instructions. How do you add here? Well, you're going to take this, and then you're going to take this, plug in the same thing to both, right, and add the results. Again, straight from the definition on the previous page. That's what it means to add two linear transformations. And then I guess I'm doing this after all. What does it mean to multiply two linear transformations? Well, multiply means compose. Likewise here, multiply means compose. And we're done, right? We have confirmed, direct calculation, these things are always equal. They're identical. And therefore, these two things are equal as functions. Okay, so that's the process. You can do this same process for a selection of these other properties, and off you go. Okay. All right. So these are our basic tools of the algebra of linear transformations. We have properties of our basic tools in this algebra, and now I'm going to start building up some machinery. There's a fair amount of machinery that has to get built up, so bear with me on this. We're going to build up some powerful machinery, and then having built up that machinery, then we're going to start doing things with it. We're going to start crushing old results once we have the powerful machinery. Okay, so here we go. Reminder. Remember that D linear transformation we talked about. The act of differentiation, right, is a linear transformation. Okay. Here's one that we didn't actually talk about quite exactly, but I think this is another pretty easy pitch. This thing I'm calling TG. This TG function says we're going to take a fixed function G, that's part of the definition of this TG. That fixed function, we're going to multiply by that function. So you can think of TG as the act of multiplication by G. And I claim, y'all can prove this on your own, a good little practice problem, the act of multiplication by G is a linear transformation. Easily checked. Okay. All right. Okay. Now, with that, notice we have kind of some atomic tools to build up a way of representing an old linear transformation we've already talked about. So specifically, y'all remember this linear transformation L. That linear transformation L, that was a tool for representing, the whole left side of our differential equation. L was, L's a lot of stuff, right? L says, you're going to have this y, okay, and you're going to do a lot of things to it. You're going to multiply it by this Q0 function. You're also going to take that y, you're going to take its derivative and multiply by this function called Q1. You're also going to take that y and take a couple of derivatives and blah, blah, blah. You're also going to take that y and take the nth derivative of it and multiply that nth derivative by this Qn function. And you're going to add all those things together. So there's a whole bunch of stuff that goes into that little monster, right, called L. But we proved back in chapter 4 that this is a linear transformation. The neat observation we're making here is that I can reinterpret that whole thing, right, this L, I can reinterpret that L in terms of the above two linear transformations, D and TG. It is what you get when you add these terms. Notice, just as for example, this thing says we're going to take y, we're going to take this y here, we're going to take n derivatives of it. Okay, well, let's take n derivatives of it. And then let's multiply by this function called Qn. Right, so there you go. That thing gives you that term right there. It's just, it just does, right? So when you add up these linear transformations here, you're getting the original linear transformation that we called L. Now, the reason we care about this, now many details to follow, but just an approximate picture of why we care about this is that there's a lot of stuff that we did with L, did a lot of things with it, and L was this kind of cryptic name that we gave to this very important thing that we need to understand in great detail. When you give a simple name to something, you're kind of concealing what's going on inside it. Right? So what we now have, we have a way to algebraically represent what is inside of this L linear transformation. This L is not just it's black box magic object that does great things. No, now we can see what's inside of it. L is made up out of these other linear transformations that I've expressed in the language of algebra, susceptible to algebraic tools. And we're gonna hit it with a hammer, crack it open, and see what's inside and see what makes it tick. And that's why this is important. It's a foot in the door to understanding L in greater detail. Okay. Alrighty. Now, a quick observation about notation. This notation that I used here, I wanted to emphasize, and I was following the book's lead on this. I wanted to emphasize that this action of multiplication by G, I wanted to emphasize that it is a linear transformation. After all, we're combining it with other linear transformations to create a pre-existing linear transformation. It was very important to understand that this is a linear transformation. Now that that's established, this is actually easier notation to just say, multiply by G. There it is. It's G. We've already got notation for how to multiply by G. You just write it down, right? So I'm going to, at this point, kind of abandon this notation pretty much and just use this notation like this. So the punchline is this gets rewritten as that. And if you're uncomfortable with this, let's again take a look at what one of these terms does. Let's look at this. What does that do? T, Qn, d to the n, y gives me, Qn times the nth derivative of y. What, on the other hand, would I interpret this to mean? Well, I would interpret that to mean, well, got a q in there, and multiply by the nth derivative of y. Right? So notice it's very natural to interpret these things as being the same thing. And this is just easier to write down. Okay. All right. Okay. All right. The next observation is kind of a quickie. We've already made this observation before, but solving a homogeneous differential equation, that's chapter 4 talk. That's kind of analysis talk. We've got, derivatives and equations, and we're looking for solutions. That's all kind of analysis talk. But remember, you can say this in linear algebra language, you might say. We're looking for a kernel of a linear transformation, that linear transformation that we've just rewritten. That's just a reminder. Okay. Here's where it gets weird. If it's not weird enough for you already. This is going to look super creepy. I claim that L is equal to P of D. Now, we got to pause on this for a second. P is a polynomial. Let me write this down just as a reminder. We've got a characteristic polynomial. P of lambda is an lambda to the n plus ... plus a0. That's our characteristic polynomial. The only things we've ever done with polynomials, right, is to plug numbers in. Right? We've plugged in real numbers. We've even plugged in complex numbers, but it remains that the only thing we've ever plugged into this polynomial, it's a polynomial. We've only ever plugged in numbers. Now, look at what I'm asserting over here. I'm claiming that I can plug in to this polynomial that thing which is not a number. Right, so you should be creeped out by that. You should, whoa, hey, slow down. What, does this make sense, or is this garbage? Is this meaningless nonsense? You can't just write symbols on the page because you feel like it, right? What does this actually mean? And, well, here's the good news. If you look at what the polynomial says, never in how we write down a polynomial does it say you can only plug in numbers. What it says is what you have to be able to do. If you're going to plug in to a polynomial, that thing that you plug in, you've got to be able to multiply it by itself a certain number of times. You've got to be able to multiply it by scalars. And you've got to be able to add these things to each other. And we can for D. I can multiply D times. I know how to multiply linear transformations at this point. We can raise D to whatever power you want. We can multiply it by scalars. We've got a scalar multiplication for linear transformations. And we can add linear transformations. So, in fact, creepy though it seems, everything you would need to do to be able to plug a linear transformation into a polynomial, we've got all of it. So, this is not garbage. Right? This is a perfectly, still weird, right? But it's a perfectly reasonable thing to want to write down, P of D. Now it remains not obvious that L actually is P of D, right? So let's, now that I've convinced you, hopefully, that that's not garbage, let me try to convince you that it actually is what I say it is. And I'll remind you first what L is. L, from chapter 4, L is an d to the n plus, etc., plus a1d plus a0. That's what L is, using the notation above. Right. Now let's see what P of D is. Let's write down a formula for P of D. P of D is, here's how you plug into polynomial P, and plugging in we get an d to the n. Reminder, this thing here that I'm plugging into the polynomial goes in, various places. Right? So you get a n d to the n plus, and then et cetera, more terms, and then a1d and a0. So p of d is that, and check it out, they're the same. I mean, it's very strange to think that this is not meaningless garbage, but this is not only not meaningless garbage, this is actually L. So, powerful observation. That characteristic polynomial, it's not just a tool for finding, roots that therefore give you a couple of solutions. That polynomial, this characteristic polynomial, describes the algebraic structure in L itself in this way. Very powerful fact we're going to see as we go along here. Okay, now I made a big deal about how multiplication doesn't commute. It doesn't, right? It certainly does not. And here's a good counterexample of failure to commute. If you look at these two linear transformations, TG and D, they just flat don't commute. I mean, because check it out. If you multiply by the TG first, then you find yourself in a situation where you're doing a product rule, and the product rule gives you two terms. On the other hand, if you were to take the derivative first, there's no product rule. You only get one term. Right? So these are clearly not equal, and so these definitely don't commute. However, notice, if your coefficients are constant, right? If this G were constant, then we're taking the derivative of a constant. That would be 0. This term goes away, and all of a sudden, these things are equal. So, wow. I mean, the good news just keeps on coming. So not only do we have an algebra that we can use to see inside of our L, linear differential operator, but it's commutative. Right? We've got addition, we've got scalar multiplication, we've got regular multiplication, and it's a commutative multiplication. So that's going to be a powerful tool. One of the main reasons for which is it's going to allow us to factor. Now, I know this keeps looking weirder and weirder, right? But everything that we're writing down, we're defining and making sense out of as we go along. So this is all actually perfectly legal. So you can factor in the same way that you factor the characteristic polynomial, like a high school algebra problem. You can factor the linear differential operator exactly the same way. It seems weird, right? But let me just point out, I'll do a quick little algebra problem here. If I multiply lambda plus 1 times lambda plus 2, I get lambda squared plus 1 lambda plus lambda times 2, and then plus 2. And the only thing that prevents me from calling this 3 lambda is, well, technically I do have to commute these and call that 2 lambda before I can rewrite this as 3 lambda. But of course, these are just numbers, and numbers do commute. So, same situation, if these are now d's, I have d squared plus 1d plus, d times 2. And again, because we're talking about constant coefficients here, the multiplication does commute. I can rewrite this as 2d, and therefore I can rewrite this product as d squared plus 3d plus 2. Now, taking that argument and turning it around backwards, what it means is you can take polynomials of D and factor them. Perfectly legal because of the commutativity. All right. Okay, so I've got a minute left. Let me use that minute. I just want to give you one punchline to this. I don't have time to prove the big results that I proved last time that have been sort of dangling since chapter 4, but I want to show you one. It's super quick. Very first thing that we did with these constant coefficient differential equations is we took a wild guess. Remember, page 1 of section 4.2. We're like, let's try exponentials, maybe? Let's see what happens if we try exponentials. And magically it worked, right? Okay, so that was super weak. right? Super lame. I just guessed the right answer. Oh, hey, look, I got lucky. And then we just kind of went on from there, right? Reasonable question. How did I know to guess that? What if you had not had that instinct to guess what happened to end up being pretty much the exact right solution? Well, there is a motivation for why it should have been the solution, and it goes like this. Now that we realize that L is not an opaque black box, but L is made up out of, well, it's a polynomial, and it's a polynomial that factors, well, I can just factor it straight up by the characteristic polynomial, just like that, right? I can shuffle these terms around however I want. Just shuffle them around in whichever way, just put them wherever they, might want to go. And now arbitrarily, having shuffled them around, let's pull out one of the factors here like this, d minus ri, whatever that root is. And I make the observation that a cheap and easy, dirty trick for solving this differential equation, if I want to make this whole thing 0, an easy way to do that is, how about I just make this 0? If I make that 0, right, if that's 0, then of course the whole left side is 0, and therefore I have a solution. And so I can solve the big nth order differential equation by solving this one differential equation, which, by the way, is y prime equals ry, namely, it's a natural growth equation. Right? Powerful idea. Using this algebra of linear transformations, we can see a free solution to an nth order problem by just looking at a specifically cleverly chosen first order problem. Its solutions are exponentials. This is why we could have reasonably expected. We didn't have these tools at that time, but these tools allow us a motivation to see why these should be solutions to the equation. We're going to get some much nicer punchlines after spring break. Have a good time and try to stay healthy. See y'all later.